In this practice, an atom in a state with L equal 1 emits photons with wavelengths of the 123 nanometers as it decays to a state with L equal 0. If the atom is placed in a magnetic field with a B equal 2 Tesla, determine the shift in the energy levels and the wavelengths. Then we'd like to find out the energies for the emissions of the photons. Energy of the photons E sub 0 can be calculated h times frequency. H is a Planck constant and F is a frequency. Hc we should use a wavelength 123 nanometers. Then you can substitute the Planck constant speed of light, and this is 123 nanometers. Then it becomes 10.1 electron volt. So atoms emit a light in the case of the magnetic field 0 by transit from the higher energy state L equal 1 state to the L equal 0 state. So this energy E sub 0 is a 10.1 electron volt. By the transitions, emissions of the lambda is 123 nanometers. Then the lowest level doesn't change, but under the B magnetic field 2 Teslas, higher energy state is L equal 1 state is split into the 3 states. Actually, we'd like to discover this U. In the middle, we know this is E sub 0. We'd like to discover this U. And then this U can be calculated. M sub L times mu sub B times magnetic field of B. You can substitute. So this is you have to multiply the M sub L. Mu sub B is a Bohr magnetons. This is a Bohr magnetons. Times B is a magnetic field. So in this case, if you want to use electron volt, Bohr magneton is a 5.788 times 10 to minus 5 electron volt per Tesla. And the B is a 2 Teslas. You need to substitute. And the ML is sometimes 1 or 0 or negative ones. So if you substitute M equals 0, it's gonna be there is no. Okay, so this corresponds to the M sub L equals 0. So if you substitute 2 Teslas in this equations, you will get M sub L times 1.1576 times 10 to minus 4 electron volt. So this is a U. U is gonna be 1.1576 times 10 to minus 4th electron volt. So compared with the E sub 0, this quantity is much smaller. Then in the question, determine the shift in the energy levels. Shift of the energy level is this U. This is a shift answer to the one of the questions, and in the wavelengths, shift in the wavelengths. So we'd like to discover the emitted wavelengths of the emitted light. This is Hc over E, energy. Energy is E sub 0 plus difference of the E. This is correspond to the E, actually U. So you can find that Hc over E sub 0 times 1 plus u over e sub 0 minus impulse. Then you can substitute u here, and the e sub 0 is a 10.1 electron volt. Then it's gonna be lambda. The answer for the lambda is a 122.999 nanometers. So in this case, delta E is a positive quantity, 1.158 times 10 to minus 4 electron volt. So the other case is 123.001 nanometers. So this is negative case, 1.158 times 10 to minus 4 electron volt. Okay, this is the answer to this practice.